Hello. In this important module, we are going to introduce heat engines, and we will do an overall analysis of an engine treating it as a closed steady systems, an analysis we have performed in the last module. Okay, so let's begin with the basic concepts of what a heat engine is. So let's say we have a system. From the dawn of civilization, we have tried to invent a system that will convert heat into work. Any device that does that. So suppose I have a system which is heated, and let's call it a hot reservoir. Let's say it's the temperature TH. The purpose of the candle is to keep this place hot. So heat is transferred to this system, and then as a result, suppose it produces external work. We'll call that net work. So we have Q dot H, the heat that goes into the system every second, and net work is produced by the system. So the conversion of heat to work in a steady state is a device that is capable of that is called a heat engine. So in this conceptual definition, we have just built a black box, which is a heat engine that is converting heat to work. So what is the simple definition of heat engine? Heat is converted to useful work, external work, at a steady state. In other words, it cannot be performed just for a few seconds. Then you can hide a battery inside a system, make a shaft turn, and say you have invented an engine. So that's the basic definition of heat engine. We want to convert heat to work. All right. So just suppose this is somebody comes to you and produces this black box and says this is a heat engine. You heat it up and it will produce net work. You understand by network what we mean is shaft work or electrical work that can be easily transferred to electricity so that you can sell it. Work is a purer form of energy. So that's a goal of civilization because shaft work was always valued. We used a horse. That's where the word horsepower comes from, to perform shaft work. And now we know that we can use the engine to do that. And for generations, scientists who tried to convert heat to work, they were called crazies, kind of. And in fact, they used to call it, we'll build a heat engine. And people used to call them engineers. So you can trace your route to this engine. When we call engineers, that was the goal of engineering. Okay, enough about history. Let's try to analyze. First rule, remember, of any system analysis, you don't want to mess with the internals. Just look at the boundary. So if we look at the boundary, what do we see? Heat is going in and work is coming out. And in this case, Q dot H is a positive number and W dot net is considered a positive number. If this engine is any good, they should be positive. Let's just clarify some definition first. The energetic efficiency that we discussed, which is desired energy output divided by required input, this takes a special name in heat engine. We call them the thermal efficiency. So what is thermal efficiency? Is basically the energetic efficiency, but we call it eta thermal. Eta thermal is defined as the network output by the required heat input. So remember, in language, any efficiency is desired output divided by required input. In this case, these are energies. So this is called thermal efficiency of an engine. Okay, so let's quickly analyze this engine. And it's working at steady state. It's a closed system. So we can quickly write the energy equation. The EDT will go to obviously 0, Q dot minus W dot external. Recall, this is the analysis we have performed when we dealt with any closed steady system. So this reduces to 0 equals q dot h is our q dot and w dot net is our external work. So that gives us q dot h must be equals w dot net, which means the thermal efficiency, which is w dot net divided by q dot h, becomes 100%. Great. So this engine, if someone comes to you and says, this is the diagram of my conceptual engine, I'm not going to let you open my blank box, but you say, okay, what happens in the boundary? And then you come up with the idea that, you know, the first law will tell you the efficiency of that engine must be 100%. There's nothing wrong with that. You know, it doesn't violate the conservation of mass or energy. But let's take a look at what happens to the second law of thermodynamics. What does the entropy equation tells us? Again, if you recall, we want to know if we draw the boundary around the heat engine to include its universe, so we can figure out how much friction is involved in this engine. Recall that this is the S dot gen universe is the measure of friction. Again, it works at steady state. ds dt goes to 0, and if we substitute q dot becomes q dot h, tb, if you recall, is th. That's what we assumed, S dot gen universe, which gives us that S dot gen universe, the measure of friction, equals negative q dot h over th. Look, q dot h is a positive number because heat is going in, and that's at the outset we said it's a positive number, and th is in Kelvin. So therefore, this is negative, which second law says friction cannot be negative. In other words, it's a measure of friction, and negative S dot gen is forbidden by second law. Basically, second law says friction cannot be negative. So even without opening up this black box, you can say this is impossible. This is an impossible engine. And sure enough, a lot of inventors come up with such engines, and this is known as perpetual motion machine of the second kind. Second kind because it violates the second law of thermodynamics. All right. Now let's go and look at a modification of the engine. So suppose someone comes up with an engine like this, that here is the temperature TH, the hot reservoir, and heat is added at a rate Q dot H. We don't have to put a candle. The source of energy can be anything: nuclear power, burning methane gas, you name it, burning coal, or solar reflectors, and it is producing shaft work, net work, and let's say we are also rejecting some heat into the cold reservoir. The cold reservoir typically is the atmosphere at Tc, Q dot C. So this is the new plan of a heat engine. So let's draw a boundary around the black box. Once again, it's a very simple definition of heat engine, that heat enters the system at a temperature TH remains constant, and produces shaft work, and heat is rejected at a temperature Tc, which is typically the atmosphere. So this temperature is kind of known most of the time. Okay, let's do a quick analysis again. So what becomes of the energy equation is Q dot minus W dot external, which gives us 0 equals Q dot H is going in, Q dot C is coming out, so that must be Q dot minus W dot net. So net work is produced. Q dot, there are two terms there. If you go through the boundary, one is positive Q dot H, one is negative. Q dot H and Q dot C are positive number. Please try to understand that. Q dot H, Q dot C, W dot net, TC, TH are all positive numbers. The arrows are telling us the direction of this transfer, but remember in the energy equation Q dot is algebraic, so we have to, Q dot H is positive, Q dot C we must put a negative sign. So that tells us W dot net equals Q dot H minus Q dot C, and that should make sense. Think about it. Think of energy flow like mass flow. If somebody says mass is coming in at a certain rate here, some is going out this way, some is going out that way, you must say for steady state Q dot H must be equals Q dot C plus W dot net. And that's exactly what the energy equation is saying. See, W dot net is the difference between Q dot H minus Q dot C, that is whatever is going in here minus whatever is rejected. The difference is the net that is coming out here. That's the simple description of the energy balance. Okay, in that case the thermal efficiency becomes, recall the definition of thermal efficiency, it's just a definition. Again, look at the denominator, try to understand that Q dot H is the required input. Q dot C is not desirable. It is just thrown away into the atmosphere. So therefore Q dot C doesn't appear anywhere. So this is our desired output for a heat engine. Heat engine's desired output is not heat. Heat is the required input. Right? And what is Q dot C? Q dot C is actually called waste heat. It's just wasted. So this is the terminology that you got to remember. So if we substitute what you got for W dot net, we get an expression for the thermal efficiency to be it becomes W dot net is Q dot H minus Q dot C divided by Q dot H. So it's 1 minus Q dot C over Q dot H. So this is true for any heat engine. And that's important to understand, not just a perfect ideal heat engine, which we are going to discuss pretty soon. So this is always valid. If you have a heat engine, if you know W dot net and Q dot H, you can find the efficiency directly. If you know Q dot C and Q dot H, then you can use this formula to find the efficiency. So try to understand this efficiency definition really fundamentally, so that you don't forget it. All right, let's do a second law analysis, just for the sake of it, to make sure second law is not violated. So we start with the entropy equation, Q dot over T boundary, recall. And now I want you to follow the next step carefully. What should be substituted for Q dot over TB? Let's look at the boundaries. Well, there is a Q dot going on here. Q dot over TB means how much entropy is carried by heat. Would you agree that the heat going in is carrying entropy and heat coming out is carrying entropy out? So Q dot over TB is, Q dot algebraically means how much heat is going in. So Q dot over TB should be split into only this boundary has a portion, this boundary has no contribution, and this boundary. So it should be Q dot over TH, and here it should be Q dot C over TC. If we put that together, it becomes Q dot H over TH minus Q dot C over TC. Please try to go over this and try to understand this, then you will really understand the entropy equation. So if the boundary has many different heat transfers, then there'll be so many terms. As a matter of fact, if the temperature of the boundary continuously changes, you have to integrate. Plus all right, so that means we can write this equation as Q dot over TC as equal q dot over h th plus okay. Now when I do this in the classroom, if I make a mistake, there are so many pairs of eyes looking at me, so I hope I don't mess up in this manipulation, but try to keep an eye on this equation. We are going to simplify this and understand what this equation says. So it says that if I manipulate this equation, say divide by q dot h both side, then we get, sorry, what we get, q dot so I'm dividing both sides by q dot h. Nothing wrong with that. And then if we multiply both sides by tc, then we get q dot c so this equation implies q dot c over q dot h must be equals tc over th plus no, we are multiplying tc, sorry, so you should multiply that by tc. All right, so the conclusion is that, well, if this heat engine is to work, we know that this term has to be positive. That's all. So far there is nothing wrong with that. All that says that, you know what, for this engine to work, you know, q dot c must be, some heat has to be rejected, which is q dot h time tc over th plus tc over q dot h time s dot gen universe. So all that is saying is that the engine will work for this to be positive. If this is positive, then there'll be some q dot c that is rejected. That's all the equation is saying. So this is a possibility. There is nothing wrong with that. So if we use this expression, take this expression and substitute in the definition of efficiency, what do we get for the thermal efficiency then? Let's take a look. Thermal efficiency of a heat engine becomes, in that case, 1 minus q dot c over q dot h. So we are substituting that. So it's 1 minus tc over th plus tc over q dot h so what we get is a very unique expression. Think about it. It says the thermal efficiency depends on 1 minus a term. All these terms are positive, right? And we know, and this must be greater than or equal 0. So notice that if there is more friction in the system, if this is bigger, in that case, the efficiency will be going down. So what is the best case scenario for an ideal heat engine? We know friction can be 0, and if we substitute this, the efficiency become ideal. For ideal engine, the efficiency become 1 minus tc over th. Well, that's a wonderful formula. Just think about it. All we need to know about a heat engine is what is its hottest temperature and what is the coldest temperature. Coldest temperature is the atmospheric temperature. You can reject heat to North Pole or somewhere weird or inside a refrigeration system. So atmosphere is our available temperature. So Tc is pretty much known, about 300 Kelvin. And Th, well, when you burn fossil fuel or something, you can pretty much guess, but you can ask any power plant, what's your maximum temperature? Then you can come up with an ideal efficiency, and you know that a real engine will have friction, and therefore its efficiency will be lower than that. This is the genius of a French scientist named Carnot. In his honor, we call this Carnot engine, and this is known as Carnot efficiency, C-A-R-N-O-T. Is called 1 minus Tc over Th. Also, notice that if this is 0, that means the engine must be reversible. If you recall our discussion of reversibility in the last chapter. So it's also known as reversible engine or Carnot engine, ideal engine, you name it. So a Carnot heat engine is reversible. What does it mean? Reversible means, remember, recall, the entropy generation is 0. That means there is no friction, there is no fingerprint of a natural process. It's ideally done. And operates between two constant temperatures. I'm sorry about this handwriting, but I hope you're listening to me. So that's the definition of a Carnot heat engine. So thermal efficiency of a Carnot heat engine is what? 1 minus Tc over Th. You cannot afford to forget this formula. It's like E equals mc square of thermodynamics. Such a simple, elegant result for such a complex problem. We don't even know yet how a heat engine operates. And yet we know what its thermal efficiency can be. Just to show you, to give you an idea of how a heat engine works, let me just quickly go over a conceptual heat engine. Again, go over these animations. It explains the same ideas we have just come across. So to explain a heat engine, this is an open cycle implementation, it's called. This is what you see in a typical power plant. So to explain, let's start with the pump. The pump, what it does is pressurizing water to a very high pressure, and then the water goes to the boiler, and there is heat coming from the heat reservoirs boiling the water. So steam is produced, superheated vapor of water is produced here as it comes out of the boiler. So this is a very high pressure, high temperature steam. As it passes to the turbine, it speeds up going through a nozzle, then it goes to a bunch of blade, making the turbine shaft turn, and that shaft work produces a lot of shaft work and produces electricity, part of which is fed back to the pump. And that's why the net work that is produced is the difference between the turbine and pump work. Anyway, so the steam that comes out is not thrown out into the atmosphere. Instead, it's recycled back. But first, it is cooled down in the condenser. And as it is cooled down, it becomes liquid. So that's why in the condenser, we need a lot of cooling water. That's why a power plant is built around a big source of water reservoir. Not because it uses water inside, which goes in a cycle continuously, but because you have to cool down that steam in the condenser. In the turbine, there's a big pressure drop. And again, this water, the liquid water, the pump raises the pressure of water. Well, that's how a heat engine works. If you just take a look at the overall boundary, you'll see the heat coming in, heat is leaving, Q.H and Q.C, and the network is produced by this. You may ask, how in the world the turbine produces more work than the pump requires? Well, that will need a little more understanding of thermodynamics, and we'll explore that when we do module 4. So let me stop here and try to go and solve a few problems on heat engines, actual engines and ideal engines, and see the difference and try to see if you can figure out the entropy generated by a heat engine.